I'm Hayawardh, and today I'm going to talk about our work on protecting resource access. So this is joint work with Xinyang, who is a PhD student at Penn State, my advisor Trent, Jaeger, and Mathias. I have since graduated and moved on to Samsung Research, and Mathias is now a professor at Purdue University. So so programs require a variety of resources to function, right? So they may require libraries, they may require configuration files, they may require log files, application data, custom files, temporary files, and so on. So how hard can it be to securely access such resources? It's just a simple open of a file name, right? Okay, so let's answer this question with an example. So I'm going to tell you a short story. At Penn State's CSE department, the web server is Apache, and they allow each student and also faculty to have their own web pages. This is quite common, right? So multiple universities have this. So when requests come into the web server, they go into the web server, and if it's for a student or faculty web page, it gets correspondingly directed. Now suppose a student turns adversarial for some reason, say, and they want to get the password file on the web server. So what could they try to do? One simple way, or one possible way, is to create a symbolic link from one of their pages to the password file, right? And then request one of their web pages and see if the password file is served instead. So in case you haven't guessed by now, the student who turned adversarial is myself, and we will see what happened. So this is just a video where I ran this same attack that I just described on our university web server. Yeah, I'm sorry, this was actually recorded, so I cannot. So, but what I'm doing here is simply creating a file, an error document actually, and then linking that to etc password. So here you see ln-s. So that's all I'm doing. And then I will go to the browser and request a non-existent page. And here you see I get back the password file of our web server, right? So what just happened? Why do these attacks continue to occur? So here, you have the web server. The web server has access to two files, among others. It has access to the password file, which is protected and indicated by the shield. And it also has access to the web pages, which are, of course, potentially controlled by adversaries. When it is going to serve a web page, it is OK to access only the adversarial files, but not something that is protected, like the password file. On the other hand, when the web server wants to authenticate users, it is OK to access only the password file that is protected, but not any adversary control files, right? So in general, we can say that what's happened here is that the program has received an unexpected resource. So it has received an adversarial one when expecting a high integrity or protected one, or vice versa. Why does this happen? So let's consider all the parties that are involved in securing a resource access. You have programmers that write code. You have OS distributors that frame access control policies. you have administrators that configure applications. Suppose the programmer sits down to write his code, and he thinks, okay, my config file and the HTML file is going to be protected by the system's access control policy. Therefore, I need not write code to protect those resource accesses, right? So that is what he does. The green ones indicate where he assumes that there is going to be no adversarial access. Unfortunately, the administrator does not know these assumptions of the programmer. So if the administrator configures a user directory or a HTML directory that is indeed accessible to adversaries, then there is a mismatch causing a problem. Similarly, if the OS access control designer, the OS distributor, makes this directory world writable, then again, there is a mismatch and a problem. So currently, these parties have no way to communicate their expectations with each other. And when problems happen, they blame each other, and the exploit goes unfixed, or the vulnerability goes unpatched. Okay, so the other reason is that even when programmers do decide to write defensive checks, they are extremely hard to get right. So suppose I want to open a file, making sure that it's not a symbolic link. Not only do I have to check for whether it's a symbolic link, I have to look at time of check to use races for inode recycling, and on top of all this, I should do it for every directory along the path, not just the final file. So how many of us write such code, right? I know that I don't. So our solution in this work is to somehow match the programmer's expectation onto the system. So whatever be the OS access control policy or the configuration, we want to make sure that the programmer's expectations are obeyed on the system. So if the programmer expects to access only protected high integrity resources, they should then only do that, and vice versa. So the latter one, of course, is the well-known confused deputy attack, where you access something adversarial, but it directs you to something that is protected, that the adversary cannot directly access. So to make this a bit more concrete, we will define 3 sets. The first set is P, which is the set of all system calls where the programmer expects something bad to happen, expects adversarial control. S is the set of system calls in the deployment where indeed something bad occurs. And R is the set of system calls that access adversary modifiable resources. So we propose 2 invariants that, if correctly calculated and enforced, will stop these attacks. The first one simply says that S should be a subset of P, which means if there is adversarial interference in your deployment, it should be at a resource access that the programmer expected to be under adversarial control. So more formally, it is this thing. And for the confused deputy, what we say is that if indeed a resource access does end up being controlled by the adversary, then it should access only resources that are also accessible to the adversary. Okay, so what is resource access? Resource access is a procedure that takes as input names and bindings, gives us output resources. So you have a program that gives a file name. The operating system uses the bindings within the OS. So these are the directories along the path. It, of course, checks the access control, and it then returns the error or a resource. Now, the problem occurs because adversaries control the inputs to the resource access, be they the name or a binding, to direct victims to unexpected resources, like we've seen. So this is the cause for these attacks. Okay, So these resource access attacks actually account for 10 to 15% of the vulnerabilities reported on the CVE database each year. And at least a subset of these have been known for a very long time. So time of check to use attacks have been known at least since 1973. Many solutions have been proposed and broken. In Oakland in 2010, Tsai et al. Came up with a claim that in order to solve these problems, if you use just knowledge that is there in the system, then you are going to end up with false positives. Meaning, if you do not also know about the program intent in making the system call, you will end up with false positives. And this is exactly what we are saying. So we are saying that you need to account for both the programmer's expectations and the system deployment where the program is deployed in order to prevent these attacks. So in this talk, we will answer two questions. The first one is, can we find the mismatches in programs due to expectations? And secondly, can we protect programs in any automated manner? So let's look at the first question. So to find mismatches, we need to reason about how the program does resource access and what the programmer expects at each resource access, right? So programmers usually, if they expect something bad to happen, they will write some protective code. If not, they do nothing. And programmers like doing a lot of nothing, as we shall see. So can we determine what the programmer's expectations were in some automated manner? You could, of course, ask the programmer to add annotations, but this is not going to help the large body of code that's already out there. But actually, there are a sort of annotation already present in the code. And this is exactly the defensive checks that the programmers write. So if you are able to find whether defensive checks have been placed around the resource access, you can then derive the programmer's expectation from that. So what are these defensive checks? These are often called filters in security terminology. So there are two types of filters, name and binding filters. Name filters, an example of a name filter is here, where you just strip an input name of .. characters to prevent directory traversal attacks. And an example of a binding filter is here, where you just check for whether the file is a symbolic link. So these are the types of filters that we want to detect. Okay, so we say that if there is no filter placed in the program, then that particular resource access should only access protected resources because it cannot handle adversarial input. So the way we go about reasoning about this in a principled manner is to build a representation called a name flow graph. A name flow graph is basically a data flow graph in which the nodes are individual resource accesses and the edges tell or indicate the flow of a name from a source resource that is used to open or fetch a destination resource. In addition, we will augment this name flow graph with filter information about name and binding filters. So we've listed in the paper an algorithm that runs over this name flow graph and can then give us output the particular resource accesses that are expected to be under adversarial control or not, essentially calculating the set P. In addition to that, it is also possible by just looking at that graph to detect likely missing filters. So for example, if a programmer has filtered the name but not the binding and vice versa, then we know something is wrong and we can output that statically. The other way of finding vulnerabilities is by actually running the program on a system and seeing if any of the resource accesses that should be protected in fact end up accessing adversarial resources. So this is the name flow graph for Apache, and we see here 3 resource accesses where the invariant S being a subset of P is violated. So these all correspond to vulnerabilities. Okay, so now the more important question, can we automatically protect such vulnerabilities from being exploited? So as we have seen, in order to protect programs against such problems, you need to consider both the program and the system deployment. And there is a system called the process firewall that we developed that does exactly this. So it looks into the program through program introspection, finds out the intent of the system call or the expectation of the system call, and limits the system call to only the appropriate resources. So you might be thinking, what if things go wrong within the program? But the reason that we can use process introspection is because we are protecting benign processes as opposed to confining malicious processes, which is what something like an intrusion detection system would do. So we rely on access control and IDSs for confinement, and then protect programs using the process firewall. So for each invariant, we have a template that will convert the rules into process firewall representations. This is an example process firewall rule. It's very similar to IP tables, if you know that. Okay, so let's move on to our evaluation. One of the most significant things we observed was that, so we evaluated our approach on 5 programs, and in 4 out of the 5 programs, more than 55% of all resource accesses, of all unique resource accesses, had no defensive checks behind them. So this means that if any of those are compromised, maybe due to a misconfiguration or access control policy being permissive, then your program is compromised. And in addition, we found 2 missing checks that corresponded to 3 previously unknown, or rather 2 previously unknown vulnerabilities and a default misconfiguration in the Apache web server. Let me quickly go through one. So Apache allows users to specify a password file to protect their pages. However, neither the name nor the binding for this is filtered. So people can specify any file they want on the system. So if I'm a user, I can as well specify the system-wide etc password. And this can be used to crack passwords because there is no rate limit on HTTP authentication, unlike normal terminal logins. And the fact that such a vulnerability remained hidden all these years shows that we need to reason about resource access in a principled manner. So this vulnerability is a very typical example of a resource access problem. Who is to blame? Would you blame the admin for not recognizing that users can be adversaries? Would you blame the OS distributor for giving a default insecure configuration? Would you blame the programmer for providing this as a configuration option in the first place? It is difficult to tell, but whatever be the case, you can use the process firewall to patch the program from the outside without requiring any cooperation from any of these parties. So in our enforcement, we had a total of around 380 rules for these 5 programs, and we verified the ability of such rules to block both the discovered vulnerabilities as well as a few previously known ones. So in conclusion, we define resource access vulnerabilities and propose principled invariants to block them. Evaluations on programs showed how programmers make a lot of assumptions about the system they're going to be deployed on. And that resource access is currently dealt with in a very ad hoc manner. And the enforcement by the process firewall shows promise. So the process firewall is available at this GitHub repository. If you have any questions, you can email me. Thank you for your attention, and I'm happy to take any questions now.
We have a little time for questions. I will start things off. So you mentioned that from the analysis you did of the CVE reports that about 10% of the vulnerabilities were resource access attacks. And I'm kind of actually surprised it's that low, because at some level, I think of all security problems being resource access problems. So I'm wondering if either the approach that you have could be expanded to cover the other 90% of ones that you're not classifying as being covered by this, or there's something about the level of the attack that is particular that this approach would target.
Thank you. So that's a very good question. So there are two things. So firstly, many attacks that are usually not considered resource access attacks are in fact resource access attacks. So there might be resources within the program that you might wish to protect. So these are traditionally not classified as resource access attacks. So yes, our approach could be expanded to a lot more classes of attacks. And secondly, we believe that many of these attacks are classified as misconfigurations and are not really reported in CVE. So, but still, if it's a misconfiguration, that is a problem and someone has to fix it. And so we believe that this is a major contribution.
Thank you.
Do we have
another question? Yeah, time for one more question.
Hey, Rob Johnson from Stony Brook. So I think this is cool work, but I do have a couple of questions. Like, when you say the process firewall can mitigate these vulnerabilities without policy changes, I'm a little confused because making process firewall rules sounds like policy changes to me. And then can you compare what are the relative, like, you know, when I think of the end game of process firewall would be that you would want these rules to ship from the vendors. So you're sort of back to where you were before. How are there advantages to using process firewall versus, say, just fixing the code?
Okay, so of course the process firewall has its own policy. So by policy here I meant the access control policy. And the fact that we have automated methods to generate process firewall policy, I think will enable people, because it's going to be unique to the deployment. So in that way, I think the automated way will enable people to deploy it easily. Thank you.
Let's thank Hayawardh again.